Now we're going to get into a topic I know a lot of students don't really like, but that's significant figures. When we measure or calculate a quantity, we have to have some indication of the precision of the measurement. So precision refers to how closely two or more of your measurements agree with each other, whereas accuracy tells us how close a measurement is to the true value. So let's look at an example. We have a piece of wire with a mass of 2 grams, and we have 3 students that measure that piece of wire. Student A measures it twice and gets an average of 1.971. Student B does the same, and so does student C. Now, if you look at the results, student A's measurements differ by 0.014 grams. Student B's measurements differ by 0.004 grams, while student C's differ by 0.002 grams. So B's results are more precise than A's because B's are more closely related to each other than student A, but student C has better precision, the 0.002. Student C is also more accurate because the average is closer to the true value of 2.000. On the loading balances in the lab, the determination of mass is reproducible to the nearest 2,000ths of a gram. So we have an error associated with those balances of 0.002. So you can write, every time you take a measurement, you can write plus or minus whatever the error is. And that's going to give you a range for your measurement. But that's cumbersome, and that takes a lot of time. There's an easier way, an alternate approach says that when you measure a quantity, all digits preceding the last are known with certainty, and the last is somewhat uncertain. So if I have a measurement, 30.822, I know this last digit is an estimate. And 30.822 has what we call 5 significant figures. So here are the rules for significant figures. Number 1, all non-zero digits are significant. So if I have a measurement, 16.2 seconds, if there's not a 0, they're all significant. 3 sig figs. Number 2, zeros placed between non-zeros are significant. 4.006, the zeros are between non-zeros, so that has 4 significant figures total. Number 3, zeros at the end of a quantity and to the right of the decimal place are significant. 12.10 meters, the 0 is significant. 4 sig figs in that measurement. Now the reason they're significant there is because if I just write 12.1, that 0 adds an extra layer of precision. So 12.1 only has 3, 12.10 has 4 sig figs. Also going along with this rule, if I have 50.00 grams, the 5 is significant. This rule says the 0 is significant, so this would actually have 4 total because everything in the middle would then be significant as well. Rule number 4, zeros to the left of the first non-zero are not significant. For example, if I have 0.0234 grams, those zeros are not significant. There's 3 sig figs. I can get rid of the zeros by putting this in scientific notation. So the zeros are placeholders in this case. They're not significant. Number 5, zeros appearing at the end of a quantity and to the left of the decimal point are not significant. 100 meters. This only has 1 sig fig. And the reason it's only 1 sig fig is more than likely this is an estimation. It's not exactly 100 meters, it's an estimate. So that's why that is not the zeros are not significant in this case. When we calculate a quantity, we have to report the answer to the correct number of sig figs. In multiplication or division, an answer can contain no more sig figs than the least number of significant figures used in the operation. So for example, go through a multiplication here. Say I want to multiply 12.34 by 1.23. When you multiply, you look at sig figs. 12.34 has 4 sig figs. 1.23 has 3 sig figs. So I'm going to get my answer from the calculator, 15.1782, but then I need to round this off. And since my least precise measurement is right here with 3 sig figs, my answer can only have 3 sig figs. My answer can only be as precise as my least precise measurement, which had 3 sig figs. When you divide, same concept. Say I want to take 10.305, I want to divide by 4.0. I'm looking at sig figs. 10.305 has 5. 4.0 has 2 sig figs. So when I get the answer from my calculator, it needs to be rounded off. 2.57625. My answer can only be as precise as my least precise measurement, so I can only have 2 sig figs. So I would report 2.6 as my answer in this division. Now with addition or subtraction, it's a little bit different. The last place retained in the sum or difference must have a significant digit in that place for each of the numbers to be added or subtracted. Let me do an addition here. Let's say I want to add these numbers together. 161.032. I want to add 5.6 and then 32.4524. Okay, the first thing I'm going to get the answer, but then I'm going to round this off. So 199.0844. But then I'm going to round this off. Now in addition, I'm looking at the number of places after the decimal. 5.6, there's one place after the decimal. There's my least precise measurement. So I can only have one place after the decimal, so I would round this off to 199.1. So in this case, my least precise measurement had one place after the decimal, and that's why I lined up the decimal places when I added these together. With subtraction, it's the same thing. With subtraction, you're looking at places after the decimal. So let's say I have 136.56, and I'm going to subtract 2.3. Okay, when you subtract, you get 134.26, but then we're going to have to round that off. My least precise measurement, one place after the decimal, so my answer can only have one place after the decimal. So I would report that as 134.3. Rounding off. If it's 4 or less, you round down, so like 7.34 rounds to 7.3. If it's 5 or greater, you round up. 7.35 would round to 7.4. There are two situations in which a number can be exact, and this occurs with defined quantities. For example, 3 feet equals exactly 1 yard. That's an exact number. It has an unlimited number of sig figs. Or if you count something rather than measure something. So if I count the number of cows in a field, that's counting. That's an exact number, an infinite number of sig figs. So how do you know if it's counting rather than a measurement? Counting is like cows, people, desks. Measurements are like meters, seconds, grams. Those are measurements you make, and these will not have an exact number. These are not an unlimited number of sig figs. We can use scientific notation for very large or very small numbers if you want to. It's just an easier way to write some of these quantities. So for example, if I have a number like 568.7 and I want to write that in scientific notation, I'm just going to move the decimal to get a coefficient between 1 and 10. So I'm going to move it there between the 5 and the 6. In this case, I move the decimal 2 places to the left. So I could scientific notation to be 5.687 times 10 to the second. It also works for really small numbers, like this number right here. If I want to put in scientific notation, I'm going to move the decimal to a coefficient between 1 and 10. So I'm going to move the decimal all the way over here after the 7. So I'm going to say 7, and then I move the decimal to the right 5 times. So it's 7 times 10 to the negative 5. So again, if you want to, with really large, really small numbers, scientific notation does help you, does allow you to actually save time in most instances. Density is one of the calculations that we perform quite often. Density is mass over volume. Very simple equation, but if I want to find the density of something, for example gold, simply have to take the mass, in this case it's in grams, divided by the volume, it's in cubic centimeters. I do need to pay attention to significant figures. We're dividing, so we're looking at sig figs. 386 has 3, 20.0 has 3. So my answer can only have 3 sig figs. So I round that off to 3 sig figs to get the density of 19.3 grams per centimeter cubed. Here are some substances and their densities at 25 degrees Celsius. Density depends on temperature. If the temperature changes, so does the density. Density of water is 1. We use that quite often. Density of aluminum is 2.7, for example. So if I put a piece of aluminum in water, it would sink because it's more dense. There are two types of properties, extensive and intensive properties. Extensive properties depend on the quantity of material. Mass and volume will change as the quantity of material changes. A property that's independent of the quantity of material is an intensive property like density. The density of water is 1.0. Doesn't matter if you have a small amount of water or a large amount of water, the density is 1.0. So density is intensive, so is color, so is melting point. Those are a couple examples of intensive properties. They do not depend on the amount of substance present.